Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel with practice problems for actuarial exams is at smarturl.it/pass actuarial exams. I teach online seminars for exams PFM, IFM, and LTAM. Information about them is at smarturl.it/btdt-online. And I wrote study manuals for these exams, PFM, IFM, and LTAM. And you can find them at the websites indicated here. So for example, for P, it's smarturl.it/btdt-p. And then for FM, it ends with FM, for IFM with IFM, and for LTAM with LTAM. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer support to our actuarial students, tax-deductible donation, you can find a way to do that at smarturl.it/help ISU actuary. This is problem number 2 from written answer section of exam LTAM given in October 2018, which was the first exam LTAM. It replaced the former exam MLC. You are given the following definition for a present value random variable. Y is equal to 0 for tx less than or equal to 5. Tx is the future lifetime of a person hx. And then it's 1000 times v to the 5th a bar angle tx plus 5, which, as you can see, indicates a life annuity at the rate of payment of 1000 per year, but payable starting 5 years from now, continuously as long as the person lives, but only starting 5 years from now if the person lives then, and then paid as long as the person lives. Part A, describe in words the benefit being valued. Well, I just told you that. B, write down an expression in terms of actuarial symbols for the expected value of y. C, you are given the following indicator in variable. I is equal to 0 if tx is less than or equal to 5, and 1 if tx is more than 5. Show that the variance of y given that I is equal to 1 is equal to 1000 squared times v to the 10th times 2a bar x plus 5 minus a bar x plus 5 squared divided by delta squared. And part 2, show that the variance of y unconditionally is given by 1000 squared times 5px times v to the 10th times 2a bar x plus 5 minus a bar x plus 5 squared, the whole quantity divided by delta squared, plus v to the 5th times a bar x plus 5 squared times 5px times 5qx. Assume now that x is equal to 65. Mortality follows the standard ultimate life table, which I will commonly write as SULT. You can find that table, by the way, at smarturl.it/SULT. And you can find the old illustrative life table used on the exams before July 2018 at smarturl.it/illustrative life table, so it's ILT. I'm sorry, smarturl.it/ILT. Deaths are uniformly distributed between integer ages. Interest rate is 5%, which is the rate in the SULT, Standard Ultimate Life Table. Part D, show that E of y is 8700 to the nearest 100. You should calculate the value to the nearest 1. Part E, Part 1, show that the probability that y is more than E of y is 0.6 to the nearest 0.1. You should calculate the probability to the nearest 0.001. Part 2, explain why the normal approximation would not be appropriate to evaluate probability that y is more than E of y. And here's the solution. So the benefit being valued is a continuous life annuity deferred by 5 years, paying at the rate of 1000 per annum, which is what I told you already. E of y, therefore, is 1000 times deferred by 5 years a bar x, which is the same as 1000 times 5ex times a bar x plus 5. For part C, y given that tx is more than 5 is 1000 v to the fifth times a bar angle tx plus 5, which is the same as 1000 v to the fifth times 1 minus v to the x plus 5 over delta, and therefore the variance of y given that tx is more than 5 is the variance of this expression we just wrote out, and that's 1000 squared times v to the 10th times, well, the last part is the standard expression for the life annuity starting at actually paid until time tx plus 5. Therefore, the variance is derived from corresponding life insurance variance, and it's just 2a bar x plus 5 minus a bar x plus 5 squared divided by delta squared. Because that's the only random part in this expression here. 1000 and v to the fifth are constants. That's why they're squared and put in front, and then all we do is this variance of this expression. And of course, 1 over delta is a constant, so it doesn't matter. So it's really the variance of v to the tx plus 5 over delta, and it's the variance of the corresponding life insurance divided by delta squared. For part C, part 2, we have expected value of y given that tx is more than 5 is 1000 v to the fifth times a bar x plus 5, and e of y is the expected value of y given I, and that's 5qx times e of y given that tx is less than or equal to 5. 5qx is the property that tx is less than or equal to 5, plus 5px times e of y given that tx is more than 5, and 5px is the property that tx is more than 5. And the variance of 0, of paying nothing, is 0, so this is, I'm sorry, not the variance, the expected value of 0 is 0, so this is 5qx times 0 plus 5px times 1000 times v to the fifth times a bar x plus 5, and the whole expression becomes 5px times 1000 times v to the fifth times a bar x plus 5. On the other hand, the expected value of y squared, given that tx is more than 5, is, well, it's a second moment. So it's the sum of the variance plus the square of the first moment. We just calculated the first moment, so we can square that. The first moment is calculated in the very first displayed formula that you see here. So the variance of y given that tx is more than 5, we calculated that before, and that's 1000 squared times v to the 10th times the variance of life insurance paid at hx plus 5, and, well, issued at hx plus 5, to be correct about that. So 2 a bar x plus 5 minus a bar x plus 5 squared over delta squared, plus the square of what we calculated in the first line that you see on this screen. And therefore, the expected value of y squared is the expected value of y squared given I. And of course, the expected value of y squared given I is the same as the expected value of y squared given that tx is more than 5. So this becomes the expected value calculation of the expression that, well, actually, I'm sorry, I didn't say this correctly. The expected value of y squared given I has two values, 0 or 1, so we have to take into account the two values. We did the calculation for I equal to 1 in the formula just above it, and the calculation of y squared given that I is 0, that's a separate thing. So anyway, this is 5qx, a property that I is 0, times the expected value of y squared, given that I is 0, so given that tx is less than or equal to 5, plus 5px times the expected value of y squared, given that tx is more than 5. And that's 5qx times 0 plus 5px times the expression we just calculated in the formula above this one. So a second to last formula, displayed formula here. And finally, the variance of y is e of y squared minus the square of the mean. Well, we plug those in. We just calculated e of y squared. We subtract the square of e of y. So we have to do a little bit of work to calculate all that, but there is a common factor in all of this, 1,000 squared times v to the 10th. And then we combine all the terms, and we get the expression that you see here. Notice that we have this peculiar expression 5px minus 5px squared, which is 5px times 1 minus 5px, and of course 1 minus 5px is 5qx. So this whole expression becomes 1,000 squared times v to the 10th times, and in the parentheses 5px times 2a bar x plus 5 minus a bar x plus 5 squared divided by delta squared, plus a bar x plus 5, little a bar, so the annuity, squared times 5px times 5qx. For part D, we have a bar 70 under a uniform distribution of deaths that's equal to 0.05 over a natural logarithm of 0.05, or I over delta, times a 70, and from the standard ultimate life table, a 70 is 0.42818, so we plug that in, and then a bar 70 is approximately 0.438797458. And e of y is 1,000 times 5 e65 times a little a bar 70, and of course little a bar 70, using the David-Ricardo formula, can be written as 1 minus big A bar 70 over delta, which is a natural logarithm of 1.05. And we just calculated a bar 70 under UDD, so we replace that. And then we can look up 5e65 in the standard ultimate life table. We'll plug that in, do the calculation, and we get approximately 8,679.11362. Now, you could also calculate the expected present value of the annuity used in the above from the formula a bar 70 under UDD equal to alpha of infinity, a double dot 70 minus beta of infinity, and all three terms on the right-hand side of the formula, this formula, are given in the standard ultimate life table. I just like David-Ricardo formula, that's why I tend to use it first, but either way is correct. For part D, since y represents the random present value of a life annuity payment, it is an increasing function of t65, and the event y being more than e of y is the same as the event t65 is more than t star, where t star is the value such that the corresponding value of y star equal to 1000 v to the 5th times a bar angle t star minus 5. So this y star, which is calculated as you see here, just by using t star in the calculation of y, satisfies the condition that y star is equal to e of y, and that is known to be 8,679.11362. Okay, so we just treat this as an equation, that y star is equal to that value, and we solve it for t star. And from that we get t star to be approximately 20.935666706. And we then calculate the probability sought using as a standard ultimate life table and linear interpolation between the values given in the table. So what is the probability that t is more than 20.935666706? What's the probability of 65-year-olds surviving this many years? So it's the ratio of L of 65 plus this 20-something, so 85.935666706 over L65, and we just do a linear interpolation between L85 and L86 to get that L85.935666706. Going from 85 to 86, the person who is 85.935666706 years old is 0.935666706 of the way already to being 86, and 1 minus 0.935666706 still at age 85. So that's the source of this linear interpolation. Now we plug in the values of L85 and L86 from the table as 61184.9 and 56.7 respectively, when we plug it in and we do the calculation, and this comes out to be approximately 0.612000955. That is actually the probability that y is more than its expected value. It's an important thing to notice that this is not anywhere close to 0.5. The probability of being more than the mean is much more than 0.5. The distribution is not symmetric about its mean. So, approximation with normal distribution is justified by the central limit theorem if the random variable approximated is a sum of many independent, identically distributed random variables. But in this case, there's absolutely no reason whatsoever to even remotely expect that. On top of that, normal distribution is symmetrical about its mean. And we just calculated y is not, as the probability it exceeds its mean is approximately 0.612, well in excess of 0.5. So it cannot be symmetrical about its mean. Please remember, this is copyrighted material. The problem itself comes from a society of actuaries. The solution is mine. Good luck in your studies and good luck on the test.